In this particular lecture, we will discuss about the degenerate time independent perturbation theory. So first of all, what the degeneracy is. So I have explained you in the lecture that degeneracy means if some energy level, right? So if some energy level have so many wave functions, which means if we calculate the energy in many different states, and if the energy came out to be just one number, then that energy level is said to be degenerate. So let us suppose this particular energy level has many state vectors like phi n1, phi n2, phi n3, and so on, and f, right? So there are these f state vectors which corresponds to just one particular energy. Okay, so here there are f state vectors. So as I explained you in the degeneracy lecture that f will be the degeneracy. So f is the degeneracy of energy level En. So this is the meaning of degeneracy, and we have discussed the degeneracy, and I explained you by using the hydrogen atom example, right? What the degeneracy mean. So this is what the degeneracy mean, right? So if you operate the Hamiltonian operator on this state, right, it will give just this energy and the state itself. So if you operate the Hamiltonian operator, the same Hamiltonian operator, let us suppose it Hamiltonian operator is S0. So if you just operate that Hamiltonian operator, and what is the meaning of operating the Hamiltonian operator? So in quantum mechanics, when you operate some operator on some state, that gives the results of the measurement. So these are the results of the measurements. So if you operate this Hamiltonian operator on this state, it will also give the same energy and the state itself. If you operate on this particular state, the result will be same. Again, if you operate the Hamiltonian operator on this state, it will give the same energy, right? So in a sense, you can write that if you operate the Hamiltonian on any of these state vectors, right? So alpha here denotes the degeneracy, the 1, 2, and so on up to f numbers. So if you operate this Hamiltonian operator on any of these states, the energy will be same, right? So let us suppose that it is En naught. So energy will be En naught always, and the state itself, right, where this alpha is 1, 2, 3 up to f, which represent the degeneracy of the state. So this is the situation when the energy levels are degenerate. So in this particular derivation I will derive again the correction term, right? Because in perturbation theory we just calculate the energy correction and the wave function correction. So in this particular derivation we are looking for those corrections, but we will start by assuming that the already solvable Hamiltonian at H naught, which is unperturbed Hamiltonian. In this case, it is degenerate Hamiltonian. That means we have many wave functions or state vector corresponding to that particular one energy. And in this particular case, we are assuming that the unperturbed Hamiltonian or exactly solvable Hamiltonian is f-fold degenerate Hamiltonian. So this is about the meaning of degeneracy, right? And for this particular type of Hamiltonian, we are going to uh, calculate the energy correction. So in this particular case, it turned out that the calculation of energy correction is not that simple, and that's why in this particular derivation we will just calculate the first order energy correction and zeroth order wave function, right? So the aim of this particular derivation is to calculate zero order state vectors or eigenstate. I will explain you what is the meaning of zero order eigenstates. And second thing that we are looking for to calculate is first order energy correction. So first order energy correction, which is En1, right? So this is the quantity that we are looking for to calculate, because the calculation for degenerate case is very hectic, very difficult. So we will just calculate these two quantities in this particular derivation. Now the let us just suppose, let the Hamiltonian of the system is h cap, right, h hat, which can be written as, so h cap, we are assuming that it can be written as hp plus, sorry, h naught plus hp cap. Again, the same story that I have told you in the starting of derivation of for time independent perturbation theory for non-degenerate case. So the starting point is just same, right? We are assuming that the Hamiltonian of the system that we are looking for can be written as the sum of these two particular terms. The one is the Hamiltonian for which we know already the solutions, right? And there is some perturbation, right? Some disturbance to the system, and we are assuming that this perturbation is very small. Again, same as we have assumed in the time independent perturbation theory for non-degenerate case. But in this particular uh, case, this particular Hamiltonian, right, is degenerate. This unperturbed Hamiltonian. So here the unperturbed, or what we can say, exactly soluble Hamiltonian H naught is F fold degenerate, right? F fold. So if you don't know what it means, you can go to the degeneracy lecture and just can understand what the F fold degeneracy mean. So we are assuming that this particular Hamiltonian is F fold degenerate. So what does that mean? I have explained you just uh, 1 minute before. So if it is F fold degenerate, then we can write it as phi n alpha is equal to En naught phi n alpha, which is very important equation. So first equation is this, second equation is this, and here the alpha is 1 2 3 4 up to f, where f is the degeneracy of the Hamiltonian, right, unperturbed Hamiltonian, and hp is perturbation, which is very small as compared to h naught, right? So these are the initial assumptions and initial basic calculations that uh, that that is important. Now what we will do, we just want to calculate the Schrodinger equation for this particular Hamiltonian. So the main problem that we are looking for to calculate, so we have to calculate the Schrodinger equation, which is H naught acting on psi n, because psi n we are assuming the new states after the disturbance is equal to En psi n, where En are the new eigenvalues. So where psi n are the new eigenstates of the disturbed system, of the perturbed or disturbed system, and En are eigenvalues of the disturbed system, right? So of the disturbed system. Okay, so this is equation number 3. This is the equation that we are gonna solve. So what we will do, first of all, you just have to remember these two quantities, right? We are looking for the zero order eigenstate and the first order energy correction. Just these quantities that we are looking for. Now you just have to solve this particular equation. Now you can replace this Hamiltonian by this particular equation because we have assumed this the Hamiltonian of the disturbed system can be written in this particular form. So from equation number 3, and 1, H naught acting on psi n giving En psi n. So we can write it as H naught Hamiltonian, right, plus Hp the perturbed Hamiltonian acting on the new states giving the new energy and the state itself. Okay, one more thing, in this particular derivation, what we will assume is that these states, right, for the zeroth order, or let me write it like this, for zero order approximation, for zero order approximation, these states can be written as, and what is the meaning of zero order approximation? So zero order approximation is that there is no disturbance. So if there is no perturbation, right, in that case the state of the system will be phi n, sorry, psi n, and this psi n, in that case when there is no disturbance, we are assuming that that can be written as the superposition of these these degenerate states. So this is the assumption that we are doing, that the zero in zero order approximation, the state of the system can be written as the superposition of this particular degenerate states, where it is a alpha, and this alpha is from 1 to f, the degenerate, all the degenerate case. So what it mean is that it is like a1 phi n1 plus a2 phi n2 and so on up to af phi n4, and this is equation number 5. Okay, so what we will do is that we will put these, the equation number 2 and equation number 5, in equation number 1, right? So now put, or putting equation number 5 and equation number 2 in equation 4, right? So what will happen, so equation number 4 can be written as h naught plus hp. Now you can replace this particular term by this particular term, so it will be summation a alpha phi n alpha, alpha is equal to 1 to f, okay, is equal to En, again summation a alpha phi n alpha phi n alpha, where alpha is from 1 to f. So now we will solve this particular equation, right? So we will solve this particular equation to get the desired quantity that we are looking for. So let me just make some space. Now this equation, when you will solve this equation, right? So just act these operators on this particular state. So what it will be, it will be like summation uh, a alpha, because it is just a scalar quantity, so the operator has to act on the state only. So H naught will act on phi n alpha, right? And yes, plus a alpha, and HP has to act on phi n alpha, right? And the summation is over all the alphas from 1 to f. On the right hand side, it will be the same, because there is nothing to act. En summation a alpha by n alpha. Alpha is from 1 to f. Okay. Now we know that when this particular quantity, the H naught, will act on this particular state which is already known, right? So I don't know, but we have written down that if this particular Hamiltonian will act on this particular state, right? Right, so it will give us E n naught, and the state itself, it is summation over alpha from 1 to f plus a alpha h naught, sorry h naught, it is hp, it is not h naught, acting on phi n alpha equal to E n summation from 1 to f a alpha phi n alpha. Now what you have to do, you just have to multiply this equation by bra phi beta, right? And beta is some another state, right? So it is just the those states which are the degenerate states. It is just that it is different from alpha, right? So what it will be, because this is just the scalar quantity and there it is the same scalar quantity, so we can take them as common. So this particular bra vector will act on this state, or we will be in the product with this particular state. This is scalar quantity, so it will be out of the product, and these two states will be multiplied. Again, here it will be phi n beta hp phi n alpha, and this particular quantity has been taken as common, is equal to En, and summation a alpha phi n beta phi n alpha at summation over alpha from 1 to f. Here it is same. So this is the equation. Now these phi alpha and alpha are orthogonal state. Again, these are our assumptions, right? We are just looking for those which are orthogonal. So if they are orthogonal, right, and they these two quantities are different, right? These alpha and beta are different, or it may be same, but the dot product of these two states will be the Kronecker delta. So it will be alpha from 1 to f E n naught, and this particular product will be the Kronecker delta, and I think that all of you have studied about the Kronecker delta. Its value is 1 when these two indices are same, and its value is 0 when these two indices are different, right? So you must have studied about them. This is just as it is, phi n beta hp phi n alpha into a alpha, and here it is just the same. So it is sorry so it is En summation a alpha, and it will be Kronecker delta, which will be delta alpha from 1 to f. Why we are doing all these calculations? Because we are looking for these two quantities, right? So this is the goal of the whole derivation, right? We just want to get these two quantities, so the whole calculation is just to get those quantities. Now what you have to do, you just have to sum over all these states. When alpha is equal to beta, then this particular polynomial delta will give us the value of 1. When it is 1, there will be this En, and if it is not equal to beta, right? So in most cases, or in all cases except 1, alpha will not be equal to beta, and for all those values this delta will be 0. So there will be just one term in the summation, which is En a when alpha is equal to beta, right? So it is, so the first term will be En naught, and it will be when the value of alpha is beta. So it will be only when the value of alpha is equal to beta. So the value of alpha is equal to beta, so not the a, right? The second term, you don't have to do anything with the second term, right? Just sum over all these states. So it is summation phi n beta hp phi n alpha into a alpha, and it is from alpha to 1 to f. On the right hand side, when you will sum up all these values, the only value which will survive will be when alpha is equal to beta. For other values, this delta will be 0. So on the right hand side, it will be like En a beta, right? So this is the equation. You have to just think about it, why it is so. It is just very simple arguments. Now what you can do, you can take this particular value on that side, or you can just take this particular value on this side. So it will be like sum over phi n beta hp phi n alpha, and the sum is from alpha 1 to f, and it will be plus En naught minus En into a beta is equal to 0, right? So we are just supposing two terms. So let us suppose this particular quantity, which is phi n beta hp phi n alpha, is equal to hp beta alpha, or alpha beta, right? And En minus En naught is equal to En1, right? So this is the quantity that we are looking for. Now what we are doing, we are just calculating up to the first order correction. So the total energy will be the sum of the already known energy and this first order correction. So if you just want to calculate the first order correction, it will be the total energy minus the already known energy of the system. So it will be the first order correction. Now just use these two equations in this particular equation, and it will be used to these two equations in this particular equation. So this particular quantity is this, right? And this, the negative of this particular quantity is this. So the equation will be like summation over alpha from 1 to f, and this will be h p alpha beta, right, minus En1 into a beta is equal to 0. Now you can write this equation like this. Alpha is from 1 to f, it is hpp alpha beta, minus you can write this term as summation over alpha from 1 to f En1 a alpha and delta alpha beta, because when alpha is not equal to beta, this term will give 0, right? When alpha is equal to beta, then this term, right, this term will be converted into this particular term. So it is just a way to write it, because we just want to take this summation as common. So now it will be hp alpha beta minus en a alpha delta alpha beta, right? So one more term that I am missing. Yes. So this was the term that I was missing. There was this a alpha there with this particular term. So there is this a alpha, right? So in this particular equation there is this a alpha. Here it is a alpha. Again there is a alpha there. It is equal to 0, and you can write it like this: a summation over alpha from 1 to f hp alpha beta minus en1 delta alpha beta, and this a alpha can be taken as common, which is equal to 0. So this is very important equation. Now what you need to do is that you have to solve this particular equation, right? So if you want non-vanishing these coefficients, right? If you just want to solve this particular equation, these are f equations, not only one equation. So if you want to solve these f equations for non-vanishing a alpha, right? Non-vanishing a alpha. For that, because the whole equation is equal to 0, and if you want this a alpha to be non-vanishing, non-zero, then this particular term, the denominator of this particular term has to be 0, right? So non-vanishing or non-zero coefficients a alpha, the determinant of this particular term, which is h p alpha beta, right, minus en1 delta alpha beta has to be 0. So just think about it. These are f linear equations, and you want to solve these f linear equation for non-vanishing alphas, right? So for solving that, these simultaneous equations, now you will write this particular quantity. So it is just this alpha and beta will vary from 1 to f, okay? And this particular quantity will be 0 if alpha is not equal to beta, and if alpha is equal to beta, then this particular quantity will be 1. So just write this particular equation in terms of matrices, right? So it will be f by f matrices. There will be f rows and f columns in this particular matrix. The first term will be, put this alpha is equal to 1 and beta is equal to 1. So the first term will be AHP1 1, and if alpha is equal to beta 1 and 1, so this term will be 1 and it will be NEN 1, right? This second term, right? This second term will be 1 2, so alpha has to be 1 and beta has to be 2, so it will be 1 2, so it will be HP 1 2. But for alpha is 1 and beta is 2, this particular term will be 0, so it is 0. The third term again it will be H 1 3, and this term will be 0, and so on up to 1 F. Okay, again the second term and the last one will be A P F1 minus 0, right? So let me write the second row also. So it will be HP21, and because it is 2 1, so it will, this term will be 0, so this term will be 0, and the second term will be 2 and 2, so it is HP22, and for this particular term these are the same, so it will be minus En1 again, there will be these diagonal terms where we will have this particular quantity. Off diagonal terms we will not have any of this particular quantity. We just have these operator values. So this will be up to H B F F minus E n 1, which has to be equal to 0. So this is very important determinant which you have to solve, right? Because when you will solve this particular determinant, because these are just the values that we know the value of this particular quantity. What is the value of this particular quantity? So we know that we have assumed this HP alpha beta is phi n beta HP phi n alpha. So we already know these quantities, right? Because we know these already solved states, and we will be given in the problem the Hamiltonian. So we know this particular quantity, how to calculate it. We don't know these energies, and this is the quantity that we are looking for, right? So we will get this particular quantity after solving this equation. So what will happen is that after solving this particular determinant, so after solving our equation, this particular equation, we will get the polynomial equation or polynomial equation of degree f. Why? Because these are this particular determinant is f by f determinant in En1, right? So the polynomial equation will be of degree f in terms of En1, and these are the quantities that we are looking for, right? So after solving this particular polynomial equation, we will get f different roots. So after solving this f degree polynomial equation, we will get f roots, right, which are the values of En1, f roots which are the values of En, right? So these are the values we are looking for. So that means we will get En, let us suppose alpha 1, or alpha is equal to 1, 2, 3 and up to f. So these roots we will get after solving this particular determinant, and we are not going to do any of the further calculation. We will do this type of calculation for particular questions like hydrogen atom, the helium atom and so on, but we will not generalize any of the calculation, right? So in general what you have to do in the perturbation theory is that you have to solve this particular determinant to get the polynomial, the fth order polynomial or degree polynomial in En1, and from that polynomial you have to calculate these roots, the f roots, right? Those f roots are the first order correction in energy. So those roots are the first order correction which we are looking for. So there is no direct formula. We have to do all these calculations to get this particular quantity, right? So once we will get this particular quantity, these particular quantities, we know that the total energy of the system is written as En naught plus lambda times En1, and we will get these quantities, right? So we will get these quantities as En alpha 1 for which the alpha is 1 to up to f. Now in general, right, so in general these E alpha 1 are real It is not the restriction that they has to be real. That is just the roots of the polynomial. So it can be complex, can be real, but in general they are real, and also they are real and different. Again, it is not at all the restriction that they has to be different. They can be different, right? Many of them are same, but some are different, right? So if let us suppose it is the fourth order polynomial, 4-degree polynomial, so it may be that two of the roots are same and two other are different, so it may be the condition. But in general, if they are different, then we will have n the f different energies of the system. So initially the energy was degenerate, sorry, f different energies, right? So in general these are different. So when you will add different quantities to this ground state, not the ground state but the exactly soluble, the energy of the exactly soluble state, if you add these different quantity, you will get different energies. So the energies are different, and corresponding to these different energies there will be different eigenstates, and hence perturbation removes the degeneration. How it is removed, again very important question, because initially this energy, this particular energy having n f degeneracy, which means there are f corresponding wave vectors or eigenstates, but now the total energy of the system are different. There are f different energies, right? And for different these different energies there will be different eigen states. Hence uh, the energy levels of the system are not degenerate, right? So the degeneracy of the problem has been removed just by perturbation, right? So if it is just that the energy, the previous energy, now it has been splitted. So if you have some energy level, so after perturbation applying some magnetic field, electric field, it will split in several levels. There will be no degeneracy in the system. So this is why we say that perturbation removes the degeneracy in the system. So this is the calculation that we want to do. One more thing. Um, After getting this particular quantity En, we can get these A alpha coefficients. So these quantities we can get only if we know these first order corrections. Yes, first order corrections. And if we know these particular quantities, then we can calculate the zero order eigenstates. So zero order eigenstate were like A alpha by N alpha, or alpha from 1 to f. Now after solving this equation, the previous equations, the determinant, we know these quantities. For these quantities we can calculate A alpha, and if we know A alpha we can write this zero order eigenstate. So this is what we want to do in this particular lecture.